Our world is a paradox of progress. We build, we grow, we connect. Our cities swell, monuments to human ingenuity, but they are hungry for energy. As our population climbs towards 10 billion, the demand for power is relentless, a constant, humming undercurrent to modern life. To meet this demand and avert a climate crisis, we have turned to the land. We have blanketed deserts with seas of glass and steel, harvesting the sun. We have planted forests of turbines on rolling hills, reaping the wind. These are triumphs of engineering, crucial first steps on our path to a sustainable future. But the land, our generous provider, is beginning to show its limits. The land is crowded. Resources are stretched. Cities grow faster than the energy systems built to sustain them. Solar farms compete with agriculture for the very soil that feeds us. Onshore wind competes with communities for the quiet landscapes we call home. The visual impact, the noise, the simple constraint of available space, these create friction. And yet, the world demands far more clean energy than land can realistically supply. We need terawatts of new power, an amount so vast that if we were to rely on land-based renewables alone, we would be forced into compromises we cannot afford to make. We need a new frontier, but the ocean is different. Covering over 70% of our planet's surface, the oceans are Earth's great, untapped wilderness. And out here, far from the friction of our crowded continents, the wind behaves differently. Uninterrupted by mountains or buildings, it blows with a fierce and reliable power. Out at sea, winds are stronger, more consistent, more predictable. The average wind speed just a few kilometers from shore can be double that of a prime inland location. This difference is exponential. A doubling of wind speed doesn't just double the power, it increases it by a factor of 8. And they hold enough raw kinetic energy to power entire nations many times over. For decades, we have known this potential existed. Early offshore wind farms were pioneering but modest, extensions of their land-based cousins simply placed in shallow water. They were a proof of concept. But now, a revolution is underway. Welcome to Eco-Innovatech. Today we explore the next frontier of global renewable energy, offshore wind megaprojects. This is a story of ambition on a scale never seen before. We will journey from the drawing board to the deep sea to understand the monumental challenges and groundbreaking solutions. We'll explore the engineering marvels that make it possible, from fixed bottom foundations anchored to the seabed, to colossal floating platforms that open up the deepest oceans. We'll dive into the economics, examining how costs are plummeting, and how these multi-billion-dollar projects are financed and built. We'll navigate the complex geopolitics, from the international cooperation creating cross-border supergrids in Europe's North Sea, to the strategic race for energy independence in Asia and the Americas. And we will confront the critical questions about the future these colossal machines promise, and their impact on the delicate marine ecosystems they inhabit. This is not the offshore wind of the past. This is gigawatt-scale infrastructure. A single project can power millions of homes. We are talking about turbines taller than the Eiffel Tower, with blades longer than a football field. Floating platforms the size of city blocks, anchored to the seabed by mooring systems engineered to withstand 100-year storms. We are talking about AI-driven autonomous operations that optimize every degree of a blade's pitch in real time. And a circulatory system of deep-sea cables, technological arteries spanning hundreds of kilometers to deliver this clean power to the heart of our cities. This is a new industrial revolution, taking place out of sight, over the horizon. It is a testament to human resolve, a decision to meet the greatest challenge of our time by harnessing the most powerful elemental forces of our planet. This is how the world taps the ocean's power. The defining challenge of our century is a monumental one. How do we power our modern world without destroying it? For decades, the answer seemed to lie on the horizon, etched against the sky by the familiar silhouettes of onshore wind turbines and the shimmering expanse of solar farms. These technologies were the vanguards of a clean energy revolution, our first great hope in the race to decarbonize. We celebrated every megawatt installed, every ton of carbon displaced. But as our ambition has grown from supplementing the grid to completely replacing it, a difficult truth has emerged. The very ground beneath our feet, the land we live on, is becoming the biggest bottleneck in the energy transition. To truly understand why the next chapter of this revolution is being written not on land, but on the open ocean, we must first confront the fundamental constraints of terrestrial energy. The first and most intractable problem is scarcity. For many nations, the dream of vast, sun-drenched solar fields or sprawling wind farms is a geographical impossibility. Consider densely populated, mountainous countries like Japan and South Korea. Every square kilometer is precious, already claimed for cities, industry, or agriculture. In the United Kingdom, a nation with ambitious climate goals, the picturesque countryside is a cherished national asset, fiercely protected from large-scale industrial development. And in city-states like Singapore, the concept of available land for energy generation is practically non-existent. For these nations and many others, achieving 100% renewable energy using land-based resources isn't just difficult, it's a mathematical impossibility. They have hit a hard physical limit. This scarcity is compounded by the second major challenge: the profound mismatch in energy density. Fossil fuels, for all their climate-destroying faults, are incredibly energy-dense. A single coal or gas-fired power plant, occupying just 1 or 2 square kilometers, can generate a gigawatt of power, enough for a major city. To replace that single plant with today's onshore wind technology, you would need to cover an area more than 200 times larger, a space exceeding 200 square kilometers. This isn't just an inconvenience, it's a paradigm-shifting reality. It means that for every fossil fuel plant we retire, we must find a land area the size of a city to replace it. On land, this kind of scale is not a feature. It is the enemy of progress, creating immense logistical, social, and ecological hurdles. The third problem is the quality of the resource itself. Wind is not uniform. Onshore, the wind's journey is a turbulent one. It's disrupted by terrain like hills and mountains, slowed by the drag of forests, and churned into chaotic vortices by buildings and infrastructure. This phenomenon, known as turbulence, is a silent killer for wind turbines. It creates inconsistent, rapidly changing stress loads on the blades, gearbox, and tower. The result? Reduced efficiency, as the turbine constantly adjusts to erratic conditions, and a significantly shorter operational lifespan due to increased wear and tear. The very land we build on degrades the quality of the wind we seek to harvest. Finally, and perhaps most contentiously, is the fourth barrier: people. The ideal locations for onshore wind, open, elevated, and windy, are often the same places people have chosen to live for their scenic beauty. As turbines have grown larger to capture more wind, they have become more intrusive. This creates a host of social challenges, often grouped under the term NIMBYism, not in my backyard. Residents raise legitimate concerns about the constant, low-frequency noise, the disorienting flicker of shadows cast by the enormous rotating blades, and the simple visual impact on a cherished landscape. These concerns translate into lengthy, expensive, and often unsuccessful permitting battles, stalling crucial projects for years. On land, we are asking people to live directly beside massive, moving industrial machinery. It's a conflict that was perhaps inevitable. But what if we could escape all these constraints? What if there was a place with no competing land use, no terrain to create turbulence, and no backyards to worry about? This is where the ocean completely flips the equation. Out here, the problems of the land dissolve into the sea. The wind is fundamentally different. With no obstacles for thousands of kilometers, it is stronger and far more consistent. The space is almost limitless, measured not in square kilometers, but in entire maritime zones. Community barriers are drastically reduced. Located far over the horizon, the turbines are out of sight and out of mind. And this superior environment allows us to build on a scale unimaginable on land, with turbines whose blades are longer than a football field, capturing immense power from every rotation. The impact of this superior resource quality is staggering. The capacity factor, a measure of how often a turbine is generating power at its peak rating, tells the whole story. A typical onshore turbine might achieve a capacity factor of around 35%. But take that exact same turbine and place it in the powerful, steady winds of the North Sea, and its capacity factor can soar to over 50%, even 60%. That means for every hour of the year, it generates, on average, 50% more clean energy than its land-based twin. It's not just a marginal improvement, it's a leap in productivity that fundamentally changes the economics and viability of wind power. For all these reasons, the global energy transition is undergoing a profound pivot. The initial sprint on land has revealed the limitations of the terrain. Now, the marathon will be won at sea. We are witnessing the beginning of a great migration of our energy infrastructure, from the crowded continents to the vast, untapped frontier of the world's oceans. This is why the future of clean energy is shifting from land to the sea. Offshore wind infrastructure comes in two major engineering systems. A. Fixed bottom foundations used in waters up to 1,060 meters deep. Types: monopiles, giant steel tubes hammered into the seabed. Jackets, lattice structures for deeper or rockier sites. Advantages: mature technology, lower cost, highly reliable. Limitations: only works near the continental shelf, cannot scale to deeper waters. B. Floating offshore wind, FOW. The true game changer. These turbines float on buoyant platforms anchored to the seabed. They unlock the deep water wind resources that make up 80% of global potential. Platform types: spar buoy, deep cylindrical ballast; semi-submersible, wide, stable, multi-column; tension leg platform, TLP, tension anchored for stability advantages; deployable in deep water, positioned far offshore; stronger winds, higher output; minimal visual impact challenges; high capex, complex dynamic stability; more advanced mooring plus cabling needed. Undersea power transmission. HVAC or HVDC cables send power to land, sometimes hundreds of kilometers. AI and digital twins. Every blade, gearbox, and cable is monitored with real-time sensors. Autonomous maintenance. Drones inspect blades. AUVs inspect mooring lines and subsea cables. AI predicts failures before they occur. This is modern eco-infrastructure in motion. In the quest for a sustainable future, humanity is embarking on some of the most ambitious engineering projects in history. At the forefront of this clean tech revolution is the offshore wind industry, a sector undergoing a radical transformation. This isn't just about building windmills at sea, it's about orchestrating a new global energy paradigm. The entire ecosystem, from the deepest seabed to the highest levels of the electrical grid, is being reimagined. This evolution is not driven by a single breakthrough, but by the powerful convergence of 5 defining megatrends, each one amplifying the others, pushing the boundaries of what we once thought possible. The first and most visible megatrend is a relentless pursuit of scale. Turbines are becoming truly massive. What was once state-of-the-art is now standard, with 12 to 15 megawatt models becoming the new workhorses of the sea. But the industry is already looking ahead. By 2030, we expect to see next-generation models reaching an astonishing 20 megawatts or more. To put this into perspective, these structures will soar 260 to 300 meters into the sky, taller than the Eiffel Tower. Their blades, each longer than an American football field, will sweep an area larger than a city block with every rotation. This bigger is better philosophy is rooted in fundamental physics and economics. Wind power is proportional to the area swept by the blades, so doubling the blade length can quadruple the power output. This exponential gain means that a single, larger turbine can replace multiple smaller ones. This drastically reduces the number of expensive foundations, cuts down on inter-array cabling, and simplifies the logistics of installation and maintenance. The result is a dramatic reduction in the levelized cost of energy, or LCOE, making offshore wind increasingly competitive with, and in some cases cheaper than, traditional fossil fuels. The second megatrend is the profound shift towards industrialized manufacturing. To build these giants at the required speed and scale, the industry is moving away from bespoke, project-by-project construction. Instead, coastal ports are being completely rebuilt into sprawling energy factories. These are no longer just places to load ships, they are highly efficient, series production hubs. Inside these advanced facilities, tower sections are welded by robots. Blades are cured in enormous, climate-controlled halls, and nacelles are assembled on production lines reminiscent of the automotive industry. This industrialization is key to achieving the economies of scale needed to meet ambitious climate targets. It creates a virtuous cycle. Standardization drives down costs, which in turn fuels more demand, leading to further investment in manufacturing capacity. A global race is now underway, with China, the European Union, and the United States all investing billions to scale this industrial base, secure their supply chains, and capture the economic benefits of this green industrial revolution. This leads us to the third megatrend, the integration of offshore green hydrogen production. Traditionally, the goal was to send every electron of electricity back to shore via costly subsea cables. But a new vision is emerging. What if the energy was converted right at the source? Instead of sending electricity, the turbines directly power large-scale electrolyzers housed on dedicated offshore platforms. Using the simple process of electrolysis, these platforms split seawater into its constituent elements, producing vast quantities of green hydrogen. This hydrogen can then be stored and transported globally, much like natural gas is today. It becomes a clean, energy-dense fuel, produced with zero carbon emissions. This innovation decouples offshore energy production from the limitations of the coastal grid. It allows us to tap into the world's most powerful wind resources, far out at sea, and convert that energy into a transportable molecule. This green hydrogen can then be used to decarbonize heavy industry, power long-haul transport, and provide clean fuel for a global market. The fourth megatrend is the rapid maturation of floating wind technology. For decades, offshore wind was limited to shallow waters where foundations could be fixed to the seabed. This excluded vast areas of the ocean with the strongest and most consistent winds. Floating platforms unlock this immense potential. By mounting turbines on buoyant, moored structures, we can deploy wind farms in waters hundreds or even thousands of meters deep. Pioneering countries like Japan, the UK, Norway, and Portugal are leading the charge, moving floating wind from small-scale prototypes to full commercial-scale arrays. As platform designs, from semi-submersibles to tension leg platforms, become more standardized and supply chains develop, costs are dropping dramatically every year. This technology is a game-changer, opening up new markets off the coasts of the US West Coast, Japan, and Southern Europe, and vastly expanding the global potential for offshore wind power. Finally, the fifth megatrend is the move toward intelligent grid integration. A single large offshore farm can generate enough power for millions of homes, but this immense power is variable. Integrating it smoothly into national grids requires a level of sophistication far beyond traditional power management. This is where the smart grid comes in. These advanced energy systems use a suite of technologies to manage supply and demand in real time. Artificial intelligence algorithms predict wind availability and balance the load across the network. Large-scale battery storage, both onshore and potentially on offshore barges, absorbs excess power during windy periods and releases it when the wind drops. Hydrogen buffers provide long-duration storage, converting surplus electricity into hydrogen that can be turned back into power days or weeks later. And critically, high-voltage direct current, or HVDC, supergrid connections act as energy motorways, efficiently transmitting massive amounts of power over long distances with minimal loss, even connecting the grids of different countries. Offshore wind is no longer just about power generation. It has become the anchor of a complex, intelligent, and resilient energy system, a dynamic network of hardware and software working in concert to power our world. China, the world's fastest deploying offshore market. Mega projects integrated with onshore industrial clusters. European Union. The North Sea is becoming the Saudi Arabia of wind. Multi-nation energy islands are under construction. United States deep west coast waters. Floating wind focus. Huge potential for California, Oregon, and Maine. Japan and South Korea land scarcity. Plus, deep waters make FAW essential for energy security. Australia, aiming to produce export-scale green hydrogen from offshore wind. Segment 4. Economic and climate impact. 1. Carbon reduction. Each gigawatt of offshore wind displaces millions of tons of CO2. With hundreds of gigawatts planned globally, offshore wind is a cornerstone of the net zero roadmap. 2. Economic boom. Offshore wind creates manufacturing jobs, heavy shipbuilding, port infrastructure upgrades, new engineering sectors, high-skill maintenance occupations. Entire coastal economies are being rebuilt. 3. Grid resilience. Offshore wind improves supply stability, lowers dependence on fossil fuel imports, reduces geopolitical energy risks, protects against land-based climate disruptions. The ocean becomes a pillar of national energy security. 4. New industrial ecosystems. Green hydrogen from offshore wind will power shipping, steelmaking, chemicals, fertilizers, long-haul transport. Offshore wind is not just replacing fossil energy, it is replacing fossil industries. Segment 5. The future scenario. Energy islands. Artificial islands will host gigawatt-scale turbines, battery storage, hydrogen production, subsea grid links, and maintenance hubs. Entire nations connected through offshore supergrids. Full autonomy. Next-generation floating farms will be largely unmanned. Robotics and AI enable 24/7 autonomous power plants. Global power export. Wind-rich nations will export clean power as hydrogen, ammonia, HVDC electricity, and synthetic fuels. A new global energy economy emerges. Offshore wind megaprojects are more than engineering marvels. They are the new backbone of the global energy system. The future is deep water, floating platforms, autonomous operations, and continental supergrids. The ocean is our next energy frontier, and humanity has just begun to tap its power.